Okay. Today we study section 4, Romberg integration. This section is not long, so I think I can finish my presentation today earlier, so we can leave earlier today. After this section, I still want to present section 7.5. Then next week, we turn to study numerical linear algebra. Okay. Today's topic, Romberg integration. This is a method to improve the accuracy of the composite trapezoid rule. Take a review about the composite trapezoid rule. Okay, review. Okay, this is subtopic. Okay, composite trapezoid rule. Okay, trapezoid rule is this formula. Trapezoid rule. It is b minus a over 2 f a plus f b. Then the error is negative 1 over 12. Second derivative at some point psi. Psi is between a and b. A and b. Because the error is b minus a to the third. If b minus a is large, then the error is large. So in the case, we usually divide the interval AB into subintervals. Okay, divide the interval AB evenly here into subintervals. Okay, into subintervals. Say the partition points are x0 is A, x1, x2, and xn is B. So the length of each subinterval is b minus a over n, the length h. Now write the integral. Write the integral into a sum, right? Summation. I from 0 to n minus 1. xi plus 1. And apply trapezoid rule to each integral. Then we get this formula. Yeah. We get the formula. H over 2. Apply trapezoid rule to each integral. Simplify the result. And recall that we cut the interval AB uniformly, okay, evenly. Okay, so we have this formula. 2 times summation I from 1 to n minus 1. F A plus I H. A plus I times H is xi. Xi, this is a xi. Then plus f of b. The error is minus 1 over 12. B minus a times h squared, second derivative on f, and evaluate as psi, some point psi. Okay, this is a composite trapezoid rule. Now, subtopic number 2. I want to develop the Romberg integration method. Okay, integration method. Okay. Here, let me use a different color. Let me let Tn below this part, below this number. Okay, below this number. This is a h over 2 f a to summation I from 1 to n minus 1 a plus I h plus fb. Okay. Okay. Yeah, I use this notation for this number. Let me about this Tn. Let me present one example first. Example 1. What are the explicit formulas for T1, n is 1, T2, T4, and T8. Okay, yeah. And also, and the interval AB is from 0 to 1. Okay, yeah. Let me use this example to explain something. Okay, something. Okay, yeah. Solution. T1. When n is 1, take a look at this sum. When n is 1, the upper limit is 0. The lower limit is 1. When lower limit greater than the upper limit, the sum is considered to be 0. Okay, 0. So when n is 1, the formula is this. The middle sum is 0 plus b. Yeah. So when n is 1, this is a trapezoid rule. Okay, trapezoid rule. When n is 2, when n is 2, when n is 2, it is because I assume the interval from 0 to 1. So h, recall that h is a b minus a over n. Now n is 1, b is 1, a is 0. So actually this is a n is 1, b is 1, a is 0. So h is 1, but there is a 2 here. So 1/2 f 0, a is 0, f b is 1. B is 1. Yeah. So when n is 2, h is 1/2. H is 1/2. So this is a 1/4, right? Because there is a 2 here. F a is 0. N is 2. So 2 f 1/2. Yeah, this sum is f of 1/2. Then plus f1 plus f1. Right. To compute t of 2, we need to evaluate 3 function values, but 2 of them, right? 2 of them, yeah, this one and this one, we have discard their values from the evaluation of T1. So actually we can save some work. So this is a, let me see, this guy plus this guy, then divided by 2 is T1. So this is a 1/2 T1, save some work. So to compute T of 2, we only need to evaluate the function value at 1/2. So this is a 1/2 F 1/2. Yeah. Save some work. Now let me compute T of 4. T of 4 is equal to 1/8 F0 plus 1/4. And F3/4 plus 1/8 function value at 1. Again, here 1, 2, 3, 4, 5 function values we need to evaluate, but some of them we have their values from the computation of T of 2, right? T of 2. So actually, I can write this 1/2 T of 2. Suppose I have computed T of 2, then plus save some work. Function value at 1/4 plus function value at 3/4. Similarly, T of 8 is 1/16. 0 plus 1/8. Uh, 2/8. Then the next term is 3/8 and 4/8, 5/8, 6/8, and 7/8. Then the final term. Yeah. Again, to save some work, we can use the result of T of 4. So we can write this as 1/2 T4 plus 1/8 F1/8 3/8 and 7/8. Yeah. So by this example, I explain, okay, how to save work on the evaluation of T of N. In general, we have the following. Okay, this is done. Okay, done with the example. Now, in general, it can be prove the following formula. Okay. If the interval AB now not necessary to be 0, 1, okay, a general interval AB. If the general interval AB is evenly divided into 2n, the power is n, 2n uniform subintervals. Okay. Then T 2n, yeah, T defined here, yeah, this is T. Okay, T. Now replace n by 2 to n. Okay, then in general, we can solve this equation. T of 2 to n is 1/2 t to n minus 1. Yeah, we use the result from the previous step, t of 2 to n minus 1. Then times hn. What is hn? Hn, yeah, we cut the interval a to b into 2n subintervals. So this is a b minus n over 2n. Yeah. Yeah. So hn, then summation I from 1 to 2n minus 1. The power is n minus 1. F xi is a plus 2i minus, this is not xi, it is a x 2i minus 1 times hn. Yeah. So to compare t of 2n from t of 2n minus 1, we need to evaluate 2n minus 1 function values. Okay, now with this notation, to t, with the notation t, now I am ready to present Romberg method. Okay, yeah, and let me call it. It is an algorithm, Romberg. Algorithm. Okay, algorithm. Yeah. Let's see how this algorithm improve the accuracy of the composite trapezoid rule. Okay. First, define Romberg. Okay, the first letter of Romberg. N 0. Define N0 to be T to N. T to N. Okay. Okay. Then we have R0, it is a T to 0. T1. What is T1? Yeah. T1. T1 is here. T1. It is 1/2 b minus a. R0, just the trapezoid rule. Then N0, it is a T to N. T to N by this formula. This is a N0. Then this should be N minus 1, 0. N minus 1, 0. So it is equals to 1/2 N minus 1, 0. 0. Then plus Hn summation I from 1 to 2n minus 1. Hn. Yeah, actually, this equation is this formula, the formula here. The Romberg algorithm is triangular array. Okay, Romberg algorithm. It is a R0, 0, R1, 0, R2, 0. Then say M, 0. Triangular array. Then the first column is computed by this equation. Okay. Now, second column, R1, 1, R2, 1, and ROM, 1. Second column. The third column is a RO2, 2, ROM2, and so on. It is a lower triangular array. Then the last one is a M. Right. First column, just the trapezoid rule. Okay. Then second column, more accurate than the first column. Second column improve the accuracy to the integral. And the third column improve the accuracy of the second column, and so on, and so on. Then, okay, now how to compute? First column, the entries in the first column are computed by this equation here. Then second column, then the remaining entries in this array, how to compute them? The formula is here. Yeah, formula. Yeah. The remaining entries in that triangular array is computed by this formula. Yeah, this is an entry in column M. This is an entry in column M-1. Okay, that plus 1 over 4M minus 1 times R n M minus 1 minus n minus 1 M minus 1. Yeah. By this formula to compute, the first column is computed from this equation. Now the remaining entries are computed from this equation. Okay. The first column, the entries involve the evaluation of function values. In total, from R00 to ROM0, in total, how many function values we need to evaluate? 2 to the power m, so many. So m cannot be too large. Okay, say maybe m is a modest number. That's okay. Say m is 10, 20. That's fine. You know, the computational cost is not high. If m is a large, say 1,000, that is too much. Okay, so usually m 10, 20. Okay, 10, 20. Okay. First column involve the computation of function values, but the remaining one, yeah, the entries in this part, low function value evaluation is involved just by this formula. So first column expensive in computation. Now the remaining entries just just this formula, low function value evaluation. So very fast. Then in this triangular array, each entry is an approximation to this integral. How good the approximation is? Yeah, how good? Okay, it can be proved. This integral I is equal to R log n m plus order hn. What is hn? Hn is a b minus a over 2 to n. Okay, yeah, this is a hn. Hn to 2m plus 2. So essentially, Romberg algorithm is an algorithm for the accuracy for an approximation to this integral of accuracy of any order, essentially any order. Yeah, you can increase m, m. Okay, so trapezoid, composite trapezoid rule. The order is let me see, composite trapezoid rule. The order is just 2, composite trapezoid rule. Now we can obtain any formula of any order. Okay, any order. So yeah, this actually this approach is better than Gaussian quadrature. Usually Gaussian quadrature is good enough, but you know, Romberg is better than Gaussian. Okay, because yeah, you can generate a formula of any order that you want. Okay, any order. Okay. So now the question is, what is the rationale behind this approach? Why compute R and NM by this formula? Why? Okay, let me explain. Okay. This is an analysis. Why this formula? Analysis. Okay. The analysis is from a famous formula. Okay, the formula is the Euler Maclaurin formula. Yeah. Integral 0 to 1 on some function is equal to 1 over 2 f0 f1, then plus summation k from 1 to q minus 1 a to k times a derivative on f 2k minus 1 times, then evaluate as 0 minus f 2k minus 1. Evaluate it at 1. Then plus a minus a to q f to q. Sine. Sine is a point, some point between 0 and 1. Yeah. Okay. Where the function f should be in this space 2q. 2q. Okay. 0, 1. Okay. 0, 1. Yeah. When function has derivative up to 2q, then we have this formula. Yeah, this formula. Then okay, now what is a2k? Yeah, A2K, they are constants. Okay. The AK, A2K, yeah, A2K. Those constants, A2K, are defined by the Taylor expansion of this function. X over EX minus 1. Okay, yeah. X over EX minus 1. Expand this function K from 0 to infinity. AK times XK. Yeah. Expand this function, then we have a series. Now the coefficients are the A here, and A here, and A here. Yeah. Actually, the coefficient AK, K factorial times AK. This number, usually we call it Bernoulli number. Okay, Bernoulli number. Yeah. So, yeah, actually, this formula is very important formula in number theory. Okay. How to prove this equation? How to prove this equation? If you are interested, take a look in the book. Okay. The proof is in section 7.7 about how to prove this equation. Okay. Now, to obtain this formula, this equation, we need to use this formula, the Euler formula. Okay. How? Okay. Now, to get the Romberg formula, evenly divide the interval A to B into 2n sub intervals. Assume the partition points are x0, x1, x2, and so on, xn. X2n should be, yeah, 2n. Then the integral AB can be written into a sum 2n, the number of partition points. Now minus 1. Okay, minus 1. Okay. This is not the power n minus 1, but 2 to n. Then the number minus 1. Integral xi plus 1. How about I use t here? Because the Euler formula use t. Okay. Now, for this integral, make a change of variables. Let me change back x dx. Now, make a change of variable xi plus from xi to xi plus 1. The distance is hn. Hn is b minus a over 2n. So xi plus 1 is xi plus hn. So now I make a change on the variable x. X is between xi and xi plus 1. So hn times t. Okay. Now, after I make a change of the variable, this integral becomes when t is 0, x is xi. So integral 0. When t is 1, x is xi plus 1. So 1. Then xi plus hn t. Then dx, it is hn times dt. Okay. Then we have move hn outside. Summation I from 0 to 2n minus 1. Integral f xi plus hn t dt. Okay, now for this integral, I apply the Euler formula here. Euler formula here. Then after we plug in this formula here, then some cancellations. Then we can simplify the expression as hn over 2. Why over 2? Because there is 1/2 here. Summation I from 0 to 2n minus 1. No, I shouldn't put -1 to the power. Okay. It is here 2n minus 1. F xi plus f xi plus 1. Then plus Euler formula. Then plus this sum. Plus this sum. Okay. Plus summation k from 1 to q minus 1. A to k. hn to k. Okay. Yeah. There are cancellations. After I simplify, after the cancellation, then we get 2k minus 1. A, then minus f 2k minus 1 b. Okay, now the third term in the Euler formula. Third term in the Euler formula. Then third term minus a 2m b minus a times hn 2n times derivative evaluate x sum upon psi. Okay, x sum upon psi. Yeah. Corresponding to each interval, each integral here, there is a sign, psi I. But then we take average on the derivative at psi I. Then we can pick a sign. This sign is between A and B. Now, psi is between A and B. Okay, take a look at this formula. This term, the first part is, let me see, the first part is T to N. T to N, yeah. Compare T to 2N. Yeah, T to N. Actually, T of 2N is composite trapezoid rule. Divide the interval AB into 2 to N subintervals. Yeah. This part is T of 2n. How about this part? This part, I can write it into, you see, there are many constants. This guy, constant. This guy, constant. They don't depend on h. So actually, this is a summation k from q minus 1. Let me see. This is a c 2k times h n 2k. Yeah. A c constant doesn't depend on hn. How about this term? This term, a is a constant. B minus a is a constant, so I can write it into a constant 2m times hn 2m times f 2m, then sine, right? Sine. Okay, now let me copy the formula here. So let me see. Integral. So integral. Let me integral the I use I for the integral. Then this term is a t of 2n. T of 2n. Then plus summation 1 to q minus 1. Summation k is 1 to q minus 1. Then C2k, C2k, Hn 2k, then plus C2m, Hn 2m, F2m, no, 2q, sorry. This is a 2q, 2q, sine. Right. So this is a, let me expand this sum. This is C2, Hn2, when k is 1. C4, Hn4, C6, Hn6, and so on. C2q minus 1, Hn2q minus 1, 2q, Hn2q, F2q minus 1. All right. Now, Romberg formula. How to get Romberg formula? By the Richardson extrapolation. Cancel this term. Yeah, use replace n by m plus 1, right? Then we get this formula. I is equal to 2n plus 1. 2n plus 1. (2n plus 1). And then constant h m plus 1 square. ck c4 hn plus 1 square, and so on and so on. So, but hn plus 1 is equal to b minus a, 2n plus 1. It is a 1/2 b minus a, 2n. It is a 1/2 hn. So this is actually is a cn, a c2. hn half square, ck, hn 2 to the fourth, and so on, and so on. So move the number 2 outside, so 1/4 hn square. This is 2 to the 4th C4 hn 4. Okay. Now, similar to Richardson extrapolation, we can 4 times this formula. Let me call it 2. This is 1. So 4 times 2 minus 1. Then we can cancel this term. Yeah. This is the rationale behind the Romberg. I call this Romberg equation. Yeah. That is the rationale behind this equation. Yeah, equation. So essentially, Romberg algorithm. Okay. The most expensive part is the first column. Okay. First column involves so many function evaluations. After that, then the remaining entries easy, right? Easy. Yeah. Just you don't need computer, just calculator by this formula. You can get all the entries. And each column is an improvement on the previous column. Basically, how accurate. This is the accuracy. Yeah, the error is this. Yeah. So this method essentially a method of accuracy to the integral of any order you want. You can obtain the formula from Romberg algorithm. Yeah. Yeah. Let me stop here. Stop.